This is the kind of question that the Large Hadron Collider sets out to answer. The LHC, the Large Hadron Collider, is the latest in a series of ever more powerful machines which fire particles at each other to see what happens. And the point is, as you fire particles at higher and higher energies, more and more things are produced. And by making sense of this, you can understand what the structure of these elementary particles is. The Large Hadron Collider has been in the news. What is it? Is it a large collider made of hadron? No, it's not. Is it a machine for making large hadrons collide with each other? No, it's not. It's a large machine for making hadrons collide with each other. And it really is very large. There's Banchory, there's Aberdeen. That is about how big it would be if they built it in Aberdeenshire. I may not have got it quite right, it may be, but it's that sort of size. It is a huge machine. How it works is you start with usually protons, but later on they're going to use lead nuclei, and you get them into this sort of second ring called the proton synchrotron, PS. That gets them going quite fast. And then you push them into the SPS, which is the super proton synchrotron, which gets them going really, really fast. And then you fire them in opposite directions into this big ring, so the protons are going that way and that way simultaneously at very, very high speeds round this huge ring. And at 4 places round the ring, this is all way underground, there are these 4 experiments where they're seeing what happens when the protons collide with each other at very high speed at 4 points in the ring. So huge arrays of very complex instrumentation of different kinds, so they're doing different experiments looking for different things at these 4 points on the ring. There are something like 40 million collisions every second, because these protons go around in bunches. So a bunch of protons collides with another bunch of protons, and once in a while, every other collision, every 1,000 collisions, something hits something, and something happens. And then all these incredibly complex instruments pick up what's happened and record it and send it to a computer when it seems like something interesting. That diagram there isn't actually a real picture of what happened. It's what a computer thought might have happened if the Higgs boson was produced. So very complex pattern of different particles coming out, and then they feed them into a computer and try and make sense of what's going on. And of course, what's going on is millions and millions of not very interesting things, and occasionally something that's really very, very interesting. As you go to higher and higher energies, you discover more and more particles. This energy scale on the left here, every time you go up by 1, it's a factor of 1,000. So there's 1,000th, 1 electron volt, 1,000, a million, 1,000 million, a million million, 1,000 million electron volts. And as you go on up, these different particles could be created. You've got enough energy. So you can see the maximum energy of the LHC up there, and where the Higgs boson maybe is produced. So the standard model is trying to explain the things that you see when these collisions take place. It's actually quite old. Started in the 1960s. By 1970, the standard model was virtually complete as a mathematical structure. And it was trying to explain that literally hundreds of different kinds of particles, protons and neutrons, etc., which appear in these collisions. There are 3 forces that affect these particles. You know about the electrical force, or the electromagnetic force, which attracts protons and electrons. There's the nuclear force, so-called strong nuclear force, which actually binds a nucleus together. Okay? But there's also a thing called the weak nuclear force, which is actually what causes radioactivity. If it wasn't for the weak nuclear force, these isotopes would be stable. But because of this very weak nuclear force, they can fall apart. Even the neutron actually isn't stable. A free neutron, left on its own, will decay in about 10 minutes to a proton, an electron, and the thing called a neutrino. That's the weak force acting. Inside a nucleus, it's stable, but left on its own, it decays. So there's these 3 forces. So the standard model is a model of the particles and of the forces, and it has been incredibly successful. It is very hard to find any experiment that anyone has ever done which doesn't agree with the standard model. People get terribly excited if they think, oh, we found a deviation, and then they find it wasn't a deviation after all. So, what's a hadron? Protons and neutrons are hadrons, so are pions, which I'll come to. Hadrons are particles which are made of quarks, which I'll come to, and hadrons are affected by the strong nuclear force. Hadrons are types of elementary particles that are affected by the strong nuclear force. Electrons are leptons, usually much lighter. They don't have any quarks in them, and they don't see the strong force at all. So that's the fundamental difference, that the hadrons see the strong force, the leptons don't see the strong force. And interesting, a proton does have a structure. Even though it's a tiny bit of a tiny nucleus, a proton has got 3 particles inside it. 2 up quarks and 1 down quark. And the neutron has got 1 up quark and 2 down quarks. Okay, 3 each. The up quark has got 2/3 plus, and the down quark's got minus 1/3 charge. And that works out well. The really odd thing is that these quarks only seem to exist inside the particles. You never see them on their own, which is a bit sort of suspicious, really. Right, that's the diagram I showed you before. Up on the left here, you've got the components of a proton and a neutron. There's the up quark and the down quark. And down on the left, you've got the electron and the neutrino, which is emitted when the neutron decays. It's a very, I'll come back to the neutrino later on, but it's a very light particle. So these 2 electrons, those 2 are components of hadrons. But the odd thing is that there's 2 more families of particles, not only up and down, but charm and strange, and top and bottom. And down here, a muon and its neutrino, and a tauron and its neutrino. So 3 sets of families, if you like, of particles, and they're all sort of similar. The up quark is plus 2/3, the down quark is minus 1/3. The charm particle is plus 2/3. The strange particle is minus 1/3. The top one is plus 2/3, the bottom is minus 1/3. It seems to follow exactly the same. So on the left, we've got the particles. On the right, we've got the forces, or rather the particles that, if you like, transmit the forces. Electromagnetic forces are actually transmitted by photons. It's got a little gamma up there. And you can model quantum mechanically the electrical attraction between particles by exchange of photons. The gluons are the ones that do the strong force. They're called gluons because glue, it sticks when you're very close together, but doesn't pull at all when you're a long way apart. That's like the strong force. It's very strong when you're close together, but isn't there at all. That's why they're called gluons. And on the left, we've got Z and W, which are the heavy particles which actually cause the weak force to work. And in the middle, there's this mysterious thing called the Higgs boson, which I'm going to ignore for the moment and come back to. So those are the particles of the standard model. Now it gets worse. Quarks actually come in 3 different colours. Let's call them red, green and blue. There's 3 different somethings. So they call them red, green and blue just to sort of have something to talk about. They're not really coloured at all. And the gluons are also coloured and they interact with the colours and change it. So there's a theory of the strong nuclear force involving these 3 colours. It's a bit like electric charge, but there's 3 kinds of it instead of just 1 kind of it. If you imagine the difference in a seesaw up and down, and one of these sort of complicated children's toys where there's 3 bits to it, you know, you can go in 3 directions. The W and Z bosons are how the weak force works, and the photons how the electric force works, and the neutrinos are only affected by the weak force. And the Higgs boson is a very important part of the system. It seems to be mathematically necessary to make everything else work. Now, what I want to say is that the standard model of particle physics is not just a list of particles. It is a very precise set of mathematical equations and how to apply them. This picture here gives you some idea of how the maths works. For example, up here there's the quarks on the right-hand side, and the gluons only interact with each other and with the quarks. They don't affect anything else. So the strong force only affects the quarks. Over here, the photon interacts with anything that's charged. So it interacts with the leptons, the electrons and so on. It interacts with the quarks because they're charged. It interacts with the W bosons because they're charged. Okay? But doesn't interact with itself. The Higgs boson down here interacts with everything else except the photons and the gluons. The photons and the gluons don't have mass because they don't interact with the Higgs boson. That's what the theory is anyway. Other things have got mass because they do interact with the Higgs boson. So this diagram is sort of a picture of the mathematics of the Standard Model. And it's not vague, it is very precise. And they can work out things very precisely, and the answers agree with experiment, with things like the LHC. Now here's a more detailed picture of the particles, which includes things like its masses. The masses here are sort of measured in energy, because in relativity energy and mass are equivalent. So here we have, the top left for example, the up quark, that's its mass, it's got a charge of plus 2/3, it's got a spin, it's spinning round of a half. And these top three ones, they're all the same except their masses are very different, okay? They've got the same charge and the same spin, but different masses. Down below you've got the down and the strange in the bottom, and they've got different masses, but they've all got minus a third, and minus a third, and minus a third. Down below here we've got the neutrinos, which correspond to the other leptons, and we don't know what the mass of the neutrinos is, but we know there's something. They used to think that neutrinos had no mass at all. We now know that they do have mass, but it's very small, and this is the limit. It's less than that, okay? And here we have the electron and so on. And here we have the particles that do the forces, and the weak force particles are actually very heavy. It took a long time to discover them. So there is a more detailed picture of the Standard Model. Here we have perhaps a simpler picture of two different kinds of hadron. Here's a proton. It's got up, up and down. Look, now I've coloured them, or somebody else has coloured them in. So in fact there's three different colours which together make white, if you like. Imagine a sort of, picture with three colours. The only things you ever see in nature are white. The colours are somehow hidden. So there's a proton. A pi meson, which is often seen in cosmic rays, that's only got two quarks, or more precisely, it's got an up quark and a down anti-quark. Blow me, that's not, well it is coloured, but it's coloured the opposite of blue. I haven't said much about antiparticles. An electron has an antiparticle called a positron.